This is a question under the topic of applications of differentiation. So to solve this question, you need to understand how to apply the first derivative test and second derivative test. Okay, so this question asks to determine the number of stationary points for this function and what are the nature of the points. Okay, so first of all, what's a stationary point? So a stationary point has a gradient of 0, right? So it's either a maximum point, a minimum point, or a point of inflection. Okay, so it's called stationary because at this point, right, it's neither increasing nor decreasing. It's like momentarily flat. Okay, so that's why we call them stationary points. So when they ask for the nature of stationary points, they're just asking, okay, is it a maximum point, minimum point, or point of inflection? Okay, so the first and second derivative test will help us determine the nature of these points, right? So let's start with the second derivative test. So for both the first and second derivative tests, you have to start with finding the stationary points first, right? So we know that the stationary points have a flat gradient, right? That means the gradient is parallel to the x-axis, is a horizontal line, right? For example, if it's a max point, right? So the gradient of this horizontal line is 0, right? So that's our clue to finding the stationary points, okay? The gradient is 0. So given this equation, let's find the equation of the gradient. Dy dx will be equal to 3x squared minus 12, okay? And since the gradient will be 0 at the stationary points, we just equate this to 0 and solve for x, right? So you divide both sides by 3, you get x squared minus 4, you factorize, and then by 0 product rule, x minus 2 is 0 or x plus 2 is 0, right? So there are stationary points at these two locations, right, where x is 2 or x is negative 2. Okay, so there are two stationary points. So how do we use the second derivative test to determine the nature of the stationary points? Okay, so the second derivative, by the way, this is known as the first derivative, right? That's when you differentiate the original equation. The second derivative is just simply differentiating that again. So dy square dx, d square y dx square. This is the symbol for differentiating the first derivative. Okay. So when you differentiate the first derivative, it will be 6x, right? So this is the second derivative. Okay. So what does the second derivative represent? Um, if you think about like the distance time graph, right? Uh, Distance, the relationship between distance and time. Okay. If it's a if it's a straight line going up, that means the speed is constant, right? Speed is positive and constant. Okay. And the acceleration is 0, right? The acceleration is 0 because the speed does not change, right? So the second derivative, since the differential measures the rate of change of whatever you differentiated, the first derivative would be speed, right? The original equation was distance. The first differential will be speed. The second differential will be acceleration. Okay, so how does the second differential tell us whether it's a maximum or minimum point? Okay, imagine if the distance time graph was curved or was going up like that, right? This would mean that we are accelerating, right? So the only way for if the line was curved this way, it must mean that at some point there must be a minimum point. Okay, if our distance time graph instead was shaped like that, that means we are decelerating, right? We are slowing down. So uh, that that will imply that there's a maximum point at some point. So in the first case, our acceleration is positive. So d square y dx square is positive. In the second scenario, d square y dx square is negative because this is deceleration. So that's exactly how um, the second derivative test tells us if there's a maximum or minimum point. Right? If it's positive, it's a minimum point. If it's negative, it's a maximum point. Okay, so let's apply that to this situation. Okay, so at x equals to minus 2, right? The second derivative will be 6 times negative 2, which is negative 12. Negative 12 is less than 0, right? So d square y dx square is less than 0, it's negative. So what does that mean? It means that at x equals to minus 2, the stationary point is a maximum point. Because remember, you are decelerating, so the shape of the curve is like that, right? So at some point, there's a maximum point. Okay, at x equals to 2, right? D square y dx square equals to 6 times 2, which is 12. 12 is positive, right? So d square y dx square is positive. So by the second derivative test, the stationary point at x equals to 2 is a minimum point. right? Yeah, so just add that in by second derivative test. Okay, that's it. So just note that when your second derivative is 0, this does not mean there's a point of inflection, right? It could be point of inflection, a minimum point where the minimum point is rather flat, and a maximum point where the maximum is rather flat. Okay? So when d squared y dx squared, where your second derivative equals to 0, this is inconclusive. And when it's inconclusive, it means you have to fall back onto the first derivative test. Okay? The second derivative test is not sufficient to tell you the nature of the stationary points. For the first derivative test, you would start off the same way. Okay, whether you do the first or second derivative test, you always need to locate the exact stationary points. Right? So you differentiate and then you equate it to 0, and then you find the values of x where where the gradient is 0. Okay, because you need to find the behavior of the curve at those specific points. Alright. So for the first derivative test, the idea is much simpler. Okay, so if it's like a maximum point, right? At the stationary point itself, we know that the gradient is 0. Okay, before the stationary point, right, it's upward sloping, right? So the gradient must be positive. After the stationary point, the gradient is, I mean, the curve is downward sloping, right? So the gradient must be negative, right? And then it will be different for minimum point, right? Gradient would be negative first, 0, and then positive. And then for point of inflection, it will be positive, right? 0, and then positive again, even if it's going the other way around, right? It could be a point of inflection going downwards. The gradient will be negative, 0, and then negative again. Okay? So how do you present your answer? Normally we would draw a table, right? Uh, we have x at the top row, the values of x at the top row. Okay, we divide it into 3 more columns, and then we'll put the first stationary point in the middle. Okay, in the next row we will put the values of the dy dx, the gradient, right? So this would be for where x equals to minus 2. Okay, so straight away the gradient at where x is negative 2 we know is 0 already, right? Because that's how we found the stationary point in the first place. Okay, for the column on the left, we want to find the point on the curve just before negative 2. So we will write minus 2 and then you minus a very small value. Okay, you want it to be just next to negative 2. So normally we would do minus 2 and then minus like 0.0001, make it very small. Okay, because if the value is too large, right? Okay, can you imagine like you have a minimum point and then a maximum point, and this is like negative 2, this point is negative 3, right? So if you find a point too far to the left, like let's say, oh okay, let's make this minimum point like negative 2.1. If you find a point 1 unit to the left of the maximum point, that will place you here. Okay, where x is negative 3, right? Then this will throw your gradient off, right? Because this will be downward sloping, and then your gradient here will be 0, and then downward sloping again after, right? So it will look like a point of inflection. That's why you want to choose a point very uh, a very tiny amount to the left. Okay, so that's why we subtract just like minus 0.001. Okay, and then we sub that in. So this will be like negative 2.0001. Sub that into the equation of your gradient. Minus 12. Oops. This will be 0.0012, right? Which is positive. Okay, so the gradient here is positive. And then we will find a point just to the right of it as well. So you take minus 2 and then you plus 0.0001. So this will be like negative 1.9999. So same thing, we sub that in. And it will give us a gradient of negative 0.0011 or 0.0012. Okay, so the gradient after the stationary point is negative. So clearly you can see that it forms a maximum point, right? So by the first derivative test, the stationary point at x equals to minus 2 is a maximum point. And then you just do the same for x equals to 2. At x equals to 2, draw the table, x here, dy dx, split into 3 more columns, 2. Okay, gradient at 2 is 0, If you sub one point to the left, so you take 2 minus 0.0001, that's 1.999, right? Sub into your gradient equation, you'll get negative 0.0012, and then you do the same for the point slightly to the right of the stationary point. Okay, sub into your gradient equation, you'll find that it's positive. Okay, so the point before your stationary point has a negative gradient, so it's downward sloping, right? Sorry. Then it's flat at the stationary point, and then after the stationary point, it's positive. So it's oops, negative is downward sloping. Sorry, negative is downward sloping. Then it's flat, and then it's upward sloping. So it's a minimum point. Okay, you can see, right? Downward sloping, flat, and then upward sloping. So by the first derivative test, the step point at x equals to 2 is a minimum point.